right, so I want to start now with a recap of what we did last time because it's been some time. Namely, we looked at the uniform electron gas. In particular, we're going to do page, you probably can't see that here, so I'll put it here, page 336 and following. What we did is we looked at the Hartree-Fock solution of the uniform electron gas, and we computed the correlation energy. We computed the correlation energy in that approximation. Remember, the approximation was the approximation of having a single fully anti-symmetrized Slater determinant, and per particle we found a correlation energy which was up to prefactor e squared over 2a0 given by 3 over 5 kFA0 squared. And if you go all the way back in your book and also in what we did to the very beginning, that was something that we had back there, and essentially from just the Hartree contribution. And now we have an additional contribution which is due to the exchange, which actually lowers the energy, which is 3 over 2 pi kFA 0. All right, so if we now transform variables and we write this in terms of the radius Rs. Remember, Rs was the sphere that we imagined having around each one of these electrons, so that when Rs is small, you have a high density, the electrons are close together. If Rs is large, you have a low density of electrons. You have a lot of space between individual electrons. So if we evaluate this, we saw that we get something that is about 2.21 divided by Rs over A0 squared minus 0.916 divided by Rs over A0. So this is a Taylor series here, or actually, well, I shouldn't say that. This is the Hartree-Fock answer for the correlation energy in terms of the electron radius Rs. So this is only interesting when you look at the exact answer for this problem. And I'm not going to tell you how you would actually compute that, but let's just say that this is an absolute heroic effort. It's also very important because it actually is something that is underneath all of the electronic structure calculations. When you do density functional theory and you look at the so-called local density approximation, then you want to have the correlation energy for a given electron density, and that electron density is exactly expressed in terms of this Rs. So well, if you do that calculation right, you find 2.21 divided by Rs over A0 squared minus 0.916 divided by Rs over A0 plus 0.0622 log Rs over A0 minus 0.096 plus terms which go like Rs over A0. So again, that is something that is valid only in the limit of high electron density, so small Rs. I should probably just write this explicitly. This is the small Rs limit. And I want to discuss this a little bit because the way that we have introduced Hartree-Fock theory first was as a variational ansatz that would minimize the energy of a certain anti-symmetrized Slater wave function. What you see here is that you can also get the Hartree-Fock energy in perturbation theory if you only get the terms that are up to Rs over A0, right? So in the very high density limit, or Hartree-Fock here gives you this answer. So you can actually derive the Hartree-Fock theory as a theory in the interactions, or in this case this will turn out as a theory that is valid in the high density limit only. Anyway, we're going to use this Hartree-Fock theory as a starting point to now go towards a very important topic in electronic structure theory, which is screening.